So okay students, so this will be the 15th session. Okay, so and in this session I'm going to talk about uh, the importance of region of convergence and one method to calculate the inverse, which is nothing but the partial fraction expansion. Okay, fine. So this will do. So what we did in the previous session was we saw the condition for convergence of Laplace transform, and I gave an example where the Fourier transform of a signal, right, doesn't exist, whereas the Laplace transform does. Okay, so if the impulse response of the system is equal to e power 3t into u of t, okay, of any LTI system, right, so then we can basically analyze it using Laplace transform, whereas we cannot analyze it using the Fourier transform. Okay, that's one of the major advantages, as well as the usage of symbol. Okay, so all you have to do to calculate the Fourier transform is, so if x of s has a region of convergence that includes the imaginary axis, okay, so all you have to do is substitute s equal to j omega, right? So you'll get the Fourier transform. Okay, provided the region of convergence includes the imaginary axis. So we saw that one false example where the region of convergence doesn't include the imaginary axis. In those cases, you cannot calculate the Fourier transform from Laplace transform, because on the imaginary axis the Laplace transform doesn't converge. Okay, so the value of Laplace transform goes to infinity. So when it goes to infinity, there is no point in evaluating the Laplace transform at those points. Okay, so that is what you mean by the term region of convergence. If imaginary axis exists in the region of convergence, right, then the Fourier transform as well as the Laplace transform both exist. If imaginary axis is not included, as in this case that you are seeing on the screen, okay, so the Fourier transform doesn't exist, whereas the Laplace transform exists only on these points. Okay, right, in the region of convergence that we saw. Okay, so we'll take two examples today, right? So my x of t is e power minus at into u of t. Okay, so let's say instead of taking it as x of t, I'll take it as h of t. Let's assume that this is an impulse response of some system where mod a is greater than 0. Okay, right, so when this happens, so e power minus at will be decaying for all the values t greater than 0. Okay, so if u of t was not multiplied, obviously when t is negative with a greater than 0, right, so minus of minus t will be positive, so e power something positive will go on growing. Okay, so for t less than 0 the exponential would have been growing, for t greater than 0 the exponential would have been decaying if u of t was not multiplied. In this case it's multiplied, so there are no issues there. Okay, so let's assume that this is the impulse response of some system. Okay, now I want to calculate the Laplace transform of this. So h of s, okay, I'll use the definition. So it is defined as minus infinity to infinity h of t, okay, e power minus st dt. Okay, right, so I'm going to substitute. So h of s is equal to, so 0 to infinity, since u of t is multiplied, e power minus at into e power minus st dt. Okay, so this product of exponentials I'm going to write it as e power s plus a into t, the minus sign, dt. Okay, so this will, if you evaluate it, so this will be equal to 1 by s plus a, provided when will this be equal to 1 by s plus a? When s plus a is something positive, right? So if you go and substitute in that condition, convergence condition, you will get real part of s should be greater than mod, or real part of a or mod a, right? So this will be the condition that you get. Okay, fine. Okay, so yeah, if let's say a is equal to 3, okay, sorry. So s plus a is greater than 0 implies real part of s greater than minus a. Okay, so s plus a has to be positive, so minus of positive into t will be exponentially decaying, so area goes to 0. Okay, so s plus a has to be something greater than 0, which means s has to be greater than minus a, right? So it is one way of calculating. So if you want the exact relation, you have to substitute in that convergence condition and you will get this. Okay, so this is the condition that you get, or you can calculate it from here also. So 0 to infinity e power minus sigma plus a, so assuming a is real, into t e power minus j omega t dt. So the mod of this is 1, so sigma plus a for this to converge, right, sigma plus a has to be greater than 0, so whereas real part of s is sigma, right? So this is how you get the convergence condition. Okay, so if a is equal to 3, okay, then so if I draw the s plane, okay, so this is sigma axis, this is j omega axis, so all these points, okay, so if this point is sigma equal to minus 3, all these points, okay, so if you evaluate the Fourier transform, let's say if you want to evaluate the Fourier transform at this point where this is 1, this is j times 2, right? So if you want to evaluate h of 1 plus j2, right, you will get a finite value, right? Whereas if you evaluate, let's say minus 4 plus j3, h of minus 4, okay, so minus 4 plus j3 somewhere here, right? So if you evaluate the Laplace transform of this, it might not exist. Okay, so it will not exist, right? It goes to infinity. Okay, so the the Laplace transform doesn't converge, whereas the Laplace transform converges here. Now in this case, note that the imaginary axis lies in the region of convergence, hence the Fourier transform also exists. Okay, so all you have to do to calculate Fourier transform in this case is substitute s equal to j omega, so you'll get 1 by a plus j omega, right? This example I guess we have solved in the previous session. Go back and look, so the Fourier transform will be the same. Okay, fine. Now this is the region of convergence. Okay, let's do another example. Okay, so example 9.2. So I'm going to take x of t equal to minus of e power minus at u of t. Okay, so if I u of minus t. Okay, how does u of minus t look like? So u of minus t, okay, so the term inside the bracket, if it is greater than 0, right, so minus t greater than 0 implies t less than 0. Okay, now so what happens when minus t is greater than 0? U of minus t will be equal to 1. Okay, so u of minus t will be equal to 1 when t less than 0. Okay, so whenever just as an example, so if minus 3 if minus 2 is greater than minus 3, right, so minus 2 is greater than minus 3, not less than. Okay, so when you multiply both sides by minus, so 2, the sign will change here. Okay, it becomes less than. Okay, so when you multiply both sides by minus, so the same thing I have done here. So minus t greater than 0 implies t is less than 0. Okay, so minus of 0 is same as 0. So right, so u of minus t exists for t less than 1. Okay, now in this case, okay, whatever the value of a is, so what should the value a take? A should be in this case it's minus a, so minus e power, this I can write it as e power a into minus t, right? So minus t will be positive for t less than 0, so a has to be negative, right? So a has to be less than 0 for this to converge. Okay, now let's see. Right, so if I calculate the Laplace transform of this, so x of s is equal to minus So minus infinity to 0, since it is u of minus t. Okay, I just directly substituted. So this I can write it as okay, so with a negative sign, of course. So I'm going to change, let minus t be equal to eta, which means minus dt will be equal to d eta. Okay, so minus dt is here, so this minus and this dt, so I am going to write it as d eta, and minus t will become eta. Okay, now when t tends to minus infinity, eta equal to minus t will tend to infinity, and when t tends to 0, eta will tend to 0. Okay, so if I substitute this, I'm just doing a change of variable. Okay, so e power s plus a into t, sorry, let's write eta. It doesn't matter whether I read t or not, so I'm not going to confuse you, since it's a dummy variable and it's going to vanish because it's a definite integral. So this will be d eta. Okay, so if I calculate this, so what do I get? I get, so 1 by s plus a. Now in this case, okay, in this case, right, s plus a has to be what? S plus a has to be negative, okay, because there is no negative sign here. Okay, so real part of s has to be less than minus a. Okay, s plus a less than 0 implies s less than minus a. Okay, now you can see that the Laplace transform of the previous case, right, even though both the signals are different, the Laplace transform of both the signals is the same. Okay, but they are existing in completely different regions. Okay, so region of convergence now for one signal is different from the region of convergence for another signal. So that is why when you calculate or evaluate a Laplace transform, you have to mention the region of convergence. Okay, so this is the significance of region of convergence. I hope it's very well understood by you guys. Okay, so we'll stop here and we'll start the next session on Sunday. Okay, thank you.